So in my last video, I measured the impact of the laser energy density on part density and be able to maintain a 0.3 millimeter gap tolerance. Now at the end of that testing, I ended up reducing my laser energy densities by 75%. This allowed me to maintain a 0.96 to 0.98 gram per cubic centimeter part density, as well as create functional parts that can meet the 0.3 millimeter gap tolerance. Now at the end of that video, I mentioned it'd be good to do tensile testing of the SLS printed parts at varying laser energy densities to see how much impact laser energy density would have on the tensile strength of parts. Now, when we did the laser energy density tests, we saw a decrease in part density. So we could probably make a hypothesis that decrease in part density would also be a decrease in tensile strength, but I wanted to see how much really that was. So today's video will show you the tensile tester I built and then the testing I did on the samples of the tensile bars I designed at the varying laser energy densities. So when I was looking at other folks do-it-yourself tensile testers, I wanted something that I could build for under $200 and be strong and accurate enough to measure the tensile strength of SLS4ALL, which ranges from 43 to 50 megapascals based on the research I did online. Now I came across two designs that I thought both had design elements I wanted to use. Now the first video was by Robert Cohen, as shown here, and he built a very simple tester that used a linear actuator as the pull force. Now I like this idea, and it just so happened my colleague had one that measured up to 1500 newtons at a speed of 10 millimeters per second lying around, so that saved me some dollars. And most linear actuators of this type cost around $50. Now Robert Cohen's design had some obvious design flaws in it. So I was looking at the other video, and this was from Clow42. I hope I'm saying that right. And he was actually using an S-type load cell on a manual machine vise, and then that transmitted the measured force to a digital scale. Now I like the concept of the S-type load cell, definitely for better accuracy, and so I purchased one capable of a 200 kilogram pole with a digital readout, and this cost me $129. His original Tensile holders also used pins, but he later redesigned and 3D printed holders with pockets to hold the end of each bar, which appeared to be a good approach. So I designed holders with a similar concept to hold my tensile bars. Since I have access to a machine shop, I had plenty of steel tubing to use to mount the linear actuator and the load cell components. And then this is the design I ended up with. Okay, so here's the tensile tester setup. So you got a linear actuator. This has the 1500 Newton limit on it. So it's just mounted. This came with the actuator, just mounted that. The bar here, this here is just a centering. Not only is it centered, but it gets this, it keeps it level, it's right height. And you can see then I've got the tensile bar holder on the actuator end. Then on this end here, you can see we just got a post that we centered this in the hole using some 3D printed templates to get that. So it's at the right height and centered, and you've got the S-type load cell here. It's like I said, it's rated at 200 kg, and then it just mounts into this. So like I said, the Cloud42, this was basically a version of his design. And so as you can see, then the parts here will fit down in here. Now one of the things I noticed, and then I don't really want to redesign new holders or print new ones. My bar size, it's easier just to print the bars different size. When this sits down in there, it's tight right there. You can see it's tight. So these, when they actually print, they print a little bit wider than the mill. We had some space in there, but it's taken it all up. And you'll see that when I pull these, the majority of these, here's a sample of one that pulled, they all break right there at the head. So the force of these 2 points pulling in that area, obviously that's the weakest point where it's going to break at. So when it pulls, so I'm going to have to thin out these, and like I said, right now these are about 7 mil width by about 4 mil deep, and I think I'm going to go more to a 6 mil wide by 3 mil deep, and that way it won't bottom out my actuator. So the load cell here obviously is connected to the digital readout here. We have a switch that's hooked up to the actuator, so we can go backwards and forward as we need to. And then this is my variable power supply. So what you're going to see is you're going to see me start at the 3 volt, and I'm going to pull at the rate of speed. You'll hear it, then you'll hear it kind of bind down, and it'll stop, and then I'll have to increase the voltage. Unfortunately, that increases the rate of speed, so it influences, and you'll see I'll go to 4, and it'll pull a little bit more, and then up to 5, and then finally, at the rate of speed, it'll break. These are the printed at 100% laser energy density, so basically the default that was in the system. So we're obviously, I'm building a box for this. This is the front panel, so right now that's just hooked in there, but we got a box. It'll be hold everything together. So basically you can see, put this in here. We got this, so we'll move it forward here till it slides into that gap. Just push it down in there. So as I said, it's pinching right in there. So these have to be thinner, but it gives us kind of directionally where our tensile strength is going to be at. So so let's go ahead and go over here, and you'll hear it pop. You can see there's already some pressure on this. So let's go ahead and move this, and it gets about 65 at 3. So we'll increase it to 4. And you can see we're up around 9.5 then. Increase it here a little bit more. So we're up to 120, and you can hear it kind of, it's up to 130, and you can see it's pulling back on it. So about 6 it usually, see, so that's why it's already was 130.77. So it just pulls so quick. So it's probably this number, I would say, would be closer to about 150 if I wasn't pulling so fast when I got up to 6 volts. So 130.77 for this sample here. And you can see as we look here, this one actually surprisingly, no, not surprisingly, it did. It broke right there once again. So where that pinch point is, it's breaking there. I want it to break more in the center, and I think once I thin this out and make it less thick, then I can pull it at a lower rate of speed, lower voltage, and then I think we'll be accomplish what we need to, and maybe be more accurate. But anyway, I'm going to show you the results from I did 100 density, I did 90%, and I did 75% with. Okay, so here's the results, kind of in this table here. And so I had some, let's just say probably some initial issues. So when I look at the energy density and the tensile strength of the 100%, that's when I say 100%, that's the default, it's in the system. And most of those, it looks like the part density measured a little over 1. And if you recall, I said the cross-sectional area is measuring closer to 30 square millimeters. And if you then take the force that we measured on the tensile tester, remember it can't kind of bottom out, and I kind of had to increase the voltage and so forth. So I think there's definitely some error here. But then you can see the formula here. It's just basically converting the force kilograms into newtons and then dividing by the cross-sectional area. And you can see on average the 100% density, laser energy densities pulled at an average of 44 megapascals, and then at the 90 it averaged around 42, and then the 75 it measured around 36. Now I've got a couple highlighted in yellow there. 2 of the samples didn't measure at the proper part density because they're underdosed. In other words, when the recoder came across, it didn't fill it totally with powder, and so they didn't get fully centered properly. It didn't affect the actual testing because the center section where they broke was not impacted. It was just the ends. It just impacted the part density. But I did see the tensile strength, the last one, it significantly lower than the others. And I think I eliminated that one in the result. But I think there were some issues. There was definitely some issues. We know where they were breaking. They weren't breaking in the optimal location. So I definitely, for my next set of samples, I decided to actually change the design of the tensile tester. Initially, I thought it was the pinch point on the holders. And actually, as I was reading, I realized that it wasn't necessarily, it was the sharp junction between the where I was holding it and at the point where we broke. So I redesigned those to have a larger fillet radius there, around 6 degrees, and you'll see on the next samples and actually they broke where we needed to. And I also, like I said, we then got closer to a 6x3, which also helped the tensile in terms of the pull. And I actually bought a new tensile linear actuator actually that could measure up to 3,000 newtons. It was 24 volts, so I could actually go down a lot lower voltage and a lot lower speed and be able to do a slow rate of speed, and you can see it was a lot more consistent. So let's take a look at those results. I actually only ran parts at this time at 80% laser energy density, just for one, to see if my hypothesis was correct on the design. So let's take a look at that. All right, so we've got our tensile tester set up. We've got this 24 volt now at about 5 millimeters per second. So we basically, we can probably pull these closer around the 5 volt mark at a speed much where we need. We actually tested the new design of our tensile bars. We actually made more of a radius there. It was too sharp, and that's why all these previous samples were breaking. We're breaking literally right at the neck, right there at the sharp. So it wasn't a big enough fillet there. So we ended up redesigning, making a better radius on these. And you can see here now it's a 6 degree angle. And so we printed some in PTG just to see, and you can see now that they're breaking below that neck. So that was a good sign. So now's the time. We printed some new bars. So I printed some. You'll see that these say X. So these are basically oriented along the X direction like this. And then these were printed such that they were printed in the up and down, well, not up and down, but in the Y axis. Now, these should be isotropic, so we should see pretty much, it shouldn't matter how it's oriented. Now I've made all the measurements. I've measured the density, part density. I've measured the length, width, the cross-sectional area here that we're going to need for the calculations. So let's just start with this sample here. And so we've got to move this closer. Oops, I need to set the output. And we'll get that down in there. Okay, so it's down in there. I'm gonna put this down. We're gonna see, this is the first one, the PTG. I could pull them at 4 volts. That's fine, but we're gonna start here, and then you're going to see this go up, and if it stalls out, then we'll know we need bigger. .02. All right, it still kind of broke up. Didn't break exactly on the chamfer. It actually broke below, so that's or on that fillet, so that's good. So 84.02 is our first one, and let's see. As you can see, that one literally snapped right in the middle. All right, and then once again, it broke in the middle, so it seems like that's where the strongest point is. So there could have been a defect on this first one, and you can see maybe because it broke a little bit lower. So, all right, so that's the ones in the X direction. So let's see if there's any significant difference in the Y direction. $87.4 and broke right there in the middle. So $87.4. That slower speed I think is also beneficial. Wow, 90.3. And I do believe some of these were a little bit thicker on the Y direction, so that would explain part of that. $87.9. And this one broke a little bit up there, but it's still below that fillet. So I think let's go back and calculate what the overall megapascals are for that. And but overall, I think finally I got the right speed and voltage and rate of pull, and these are finally breaking below the neck. So those are the two critical problems I was trying to solve, and it sounds like we accomplished that. Okay, so if we look at the results then of the tensile strength based on those force measurements, at the 80% of the energy density, we see that they averaged about almost 44 megapascals. And the standard deviation on this was significantly below 1, which for my other samples were much higher. So by going to a slower, smoother pull on the tensile and making sure that our tensile bars were radiused correctly and break in the middle, I think we get a really true representation. Before, when I was at 100% energy density, I kind of showed average around 44, and I said I thought it would be higher if we did everything slower and better. And at 80, we're seeing 44. So now I just need to go back and do the profile printing with 190 and so forth, just to see. But based on these results, I think I'm now going to move my energy density to around 80% of the default. I know I can still meet the tolerance cubes at that 0.3 millimeter tolerance that we need for functional parts. I get good part density at this, and I'm within that range of the tensile strength I need to be at. So I think I'm going to do some those tests, but I think just based on this, I want to kind of get this video out to show you what I measured. I think you should be pretty confident that this machine, the printing settings that I have, are hitting where we need to be at for strength of parts.